Hey gang, welcome back to 4600. Today we're going to discuss section 8.8, which is discusses what this textbook calls small sample confidence intervals, and it mainly has to do with the t-distribution. So let's kind of get into it. So back in 8.6, we were looking at confidence intervals that were for large samples, mainly the z interval for one sample or one mean, and the difference between means, and then we also used the normal distribution or the z interval technique for the proportions and the difference in proportions as well. Today we're going to turn our attention to what this textbook calls small sample confidence intervals for mu and the difference between two population means. So some things to note about this section. We're going to be dealing with the t-distribution, and this kind of goes against my thoughts on the t-distribution, the way this textbook does this. The way this textbook teaches the difference between large sample and small sample confidence intervals is that when you have a small sample, you have to kind of determine the normality of it, and then you use a t-distribution for those always. Whereas when you have a very large sample size, you can always use a z. That's technically true, all right? But a lot of technology, when you go about it, doesn't have a normal distribution or a z interval or a z test kind of thing going on with it. Most of them still run a t, because the bigger the sample size is, the t is close enough to the normal approximation that we can get away with it, okay? So that's all I'm really going to say about this. But we're going to, for this course specifically, if you have small samples, you're going to definitely do anything less than 30. You're going to do a t. You're going to use the t distribution to get your confidence intervals. So again, like I said, some things to note about this section is we will assume that the experimenter samples have been randomly selected from a normal population. All right, that's very similar regardless of whether we're doing a z interval or a t interval. The t interval, like I said, these intervals are suitable for any sample size really, but we really look at them in this section. We're going to look at them for small samples, and as long as there's not a great departure from normalcy, we can actually use the t interval to estimate the target parameter, because the distribution we will use because of the distribution we will use, we can assume that the interval estimates are robust to what we call non-normal behavior. Now this may go a little bit against what I've not really against, but I don't think I've ever really mentioned this extremely before. The t distribution itself is very robust, as they say, to non-normal behavior. And so if a data set's not exactly normal, or it's a little bit funky, you can kind of get away with the t-distribution a little bit more than you can the normal distribution, because it allows a little bit of leeway there. That's what the word robust here means. It means we have a little room to play with, and we can kind of get away with it and be a little more loosey-goosey with it, all right? And so that's kind of the point of that statement. Anyway, what kind of intervals fit these items? Well, I kind of already gave it away. It's the t interval, and here are the formulas for them. There's one more in here than is in the book, because I wanted to cover all the t intervals. If we're going to cover them, let's cover them all. The first one's the traditional one for a one sample population mean being our target parameter. This guy here. It's just y bar plus or minus. Instead of using z alpha over 2, we're going to use the t distribution's critical value, t sub alpha over 2, and then the standard deviation over the square root of n. Now note, we were able to use the sample standard deviation little s here with the large sample ones if that's all we knew when the sample was large enough, because we can get away with replacing the population mean with that there. But ultimately, some books go back and forth on this, and some people still say, if you know that's the reason I always stick with the t interval when I only know the sample standard deviation, because that's what the t interval is known as. It's called it's a confidence interval when the population standard deviation is unknown, and so we usually run a t in those cases. But this textbook kind of says you can get away with the z in those cases when your sample size is big enough. All right, I'm getting off track there. I apologize. But then we have two different versions of the confidence intervals for the difference between two means. And if you've taken me for biostats, we've actually somewhat discussed these two guys. either way, there's a bunch of different little formulas for them, and we'll kind of go through them, why we do the different ones here. But the first one here, for the mean, is this one here is sometimes called the it's just the standard difference between two means, t interval. It's when you assume that the two variances of the two different groups that you're looking at a difference from are equal to each other. That requires us to use this special standard deviation, which is a pooled standard deviation. We'll talk about that more later. Our degrees of freedom are n sub 1 plus n sub 2 minus 2, as opposed to just n minus 1. All right. And then the S pool formula is here. So it's kind of an extra little formula you got to calculate to plug in. And that's really the only difference there. We have to use a pooled standard deviation. In other words, a pooled standard deviation is kind of like an average or a weighted average of the two standard deviations from your two different samples. All right. If you assume, which most people would go with the second option here, almost always, most people will assume that the population variances are not equal to each other. If the variances are not equal to each other, then we do what they call, this is sometimes called I'm not gonna try to spell the last guy's name, but it's like the Welch-Satterthwaite, I'll just call it SATT method. The Welch-Satterthwaite method just uses a specialized degrees of freedom formula to kind of, at least technology uses this, and we'll use it in this class, where it's just the average of the two standard deviations, the sample standard deviations divided by their individual sample sizes. But the way we get our T alpha over 2 is we need to know the degrees of freedom, and it happens to be some kind of like weighted degrees of freedom that we need to use to get that. And so unfortunately it's got two-part formula here, and the degrees of freedom formula is kind of hefty itself, but before you can even calculate that, you have to calculate this value of C first. So it's a little bit of an extra step, but it's really not as bad as it looks. It's just kind of ugly from when you look at it at first. And then the T alpha over 2 value can be found using either the inverse T on your TI calculators, and very similar to the Z alpha over 2, you can do 1 plus the confidence level divided by 2, and then the degrees of freedom. Or in R, you can use the QT function and do the same thing in there. Okay. And that's pretty much all the formulas we need to construct any confidence intervals in this section. All right, so let's do a one sample variety here. So in example 1 here, a manufacturer of gunpowder has developed a new powder which was tested in 8 shells. The resulting muzzle velocities in feet per second were as follows. I'm not going to read those out, you can see them. They want us to find excuse me, they want us to find a 95% confidence interval for the true average velocity for the shells of this type. And we're supposed to assume that the muzzle velocities are approximately normally distributed. Again, that's always important with these kind of confidence intervals. So I use the one. You can either use 1-bar stats, or you can use R to calculate the statistics that you need for this. So from the 1-bar stats in your calculator, or using R, I use the R and I put in that data set on the previous slide in as a vector, and then I use the mean function and the standard deviation function to get the values that I got, and this is what I get. So there are 8 values in that data set, which means the degrees of freedom are n-1, which equals 7. And then the y-bar value, or the mean I got, was 2,959. And the I make my lines a little thicker. And then the value for S was 39.09. Okay. And then the critical level that they want was a 95%, or 0.95 confidence level. And the T alpha over 2 value is going to be, I'm going to use R again, it's QT of 1 plus 0.95 or 1.95 over 2. Comma 7 degrees of freedom, and that gives me a critical value of 2.365. So I've got everything I need. Just kind of a refresher if you haven't used R in a minute. If you're taking biostats this semester, then you're pretty comfortable using R. But if you're going to be finding R, using R to find other things, it might not hurt to just give you a quick refresher if you spend a minute since you've used R. So say I wanted to put in that data set on the previous slide, and I'll pull that back over. You won't be able to see it, but I can make a vector in here by saying x equals and use a C to create a vector, parentheses, and then you just list in the data values separated by commas. 29, 25, 29, 35, 29, 65, 29, 95, 3005, 29, 37, and 2905. Make sure I got 1, 2, 3, 4, 5, 6, 7, 8 values, and we'll know for if I put them in right in a second. Mean of x is 2959 like I got, and the standard deviation of x is 39.09 rounded to 2 decimal places. Sometimes you want to round that off a little further than that, but I just stopped there. And if you just needed the variance, which we'll need for some future procedures, it's just var, and then I could find the variance of x if I wanted to. So those are helpful and pretty quick. None of the data sets we'll give you will be terribly long anyway. Okay. So anyway, back to the problem at hand. So to formulate this one sample confidence interval, I need to do y bar plus or minus critical value times s over the square root of n. And y bar was 2959 plus or minus the critical value 2.365 times the standard deviation 39.09, and that is the sample one, divided by the square root of the sample size, which was 8. And when I do that, I get 2959 plus or minus 32.69, or the final answer should just be a 95% confidence interval for mu is equal to 2,976.3 to upper bound 2991.7, and that's feet per second. Can't forget those units. All right, so nothing exciting there, but nonetheless, it's pretty simple once you get the values you need to plug in. So that's all we're really doing today anyway. All right. So now we want to move into doing the difference between two means, but I want to talk about where the SP value comes from, and whether we get this in full or not is okay. S of P is called the pooled standard deviation. Okay. So say we have the following pivotal quantity. Sorry, I'm not talking there, but Z, you're going to use the traditional Z, the Z score formula for the difference between two means, which would be y bar 1 minus y bar 2, or y bar sub 1 minus y bar sub 2 minus mu sub 1 minus mu sub 2, all over, and we're going to assume the standard deviations are the same for this example. They're not always, but we're going to assume they are. Sigma, and I can pull all sigma out of there, and it'll just be 1 over n sub 1 plus 1 over n sub 2 inside the square root. Alright, so we're just assuming the standard deviations are the same for both groups. Well, S pooled equals the sum of I equals 1 to n of y sub I minus y bar sub I, or y bar sub 1, sorry, squared, plus the sum of I equals 1 to n of y sub 2i, y sub 1i and y sub 2i for the different groups, minus y bar sub 2 squared, all over. It's really taken, imagine these are two independent samples and we're finding the standard deviations for each. That's where the summations in the top come from. In the bottom, it would be like each one of them had their own degrees of freedom. So we're dividing by the degrees of freedom here. And it would just, we would have n sub 1 minus 1 plus n sub 2 minus 1 together. But this would end up equaling just n sub 1 minus 1 times s sub 1 squared plus n sub 2 minus 1 times s sub 2 squared. So the standard, the variance for each group multiplied by its degrees of freedom divided by the combined degrees of freedom n sub 1 plus n sub 2 minus 2. That's where the degrees of freedom in that formula I gave earlier came from. Just combining the two together. And we had shown at some point back when we talked about chi-squared in chapter 7, we talked about this giving us, in this here, giving us the two values that this equates to. So this is from the past. If you don't recall that, then maybe go back and look at that. Okay. So now we're going to do something weird. We're going to let this value w be the sum of chi-square random variables. There'll be a reason I'm doing this. Square random variables with degrees of freedom equal to n sub 1 plus n sub 2 minus 2. All right. So what happens with w is it's like we combine, we're pooling together the two standard deviations we see in the previous problem to get a chi-squared distribution, or a chi-square random variable called w, and it's going to be the degrees of freedom instead of just n minus 1 like we see here will be n sub 1 plus n sub 2 minus 2 times the pooled standard deviation squared, or the variance of the pooled standard errors, divided by sigma squared. All right. Now it looks exactly like a chi-square random variable we saw back in chapter 7. So if we take and create a t interval out of this, recall the formula for the t was a z z-score formula basically, or a z-score pivotal quantity divided by the square root of a chi-squared random variable with new degrees of freedom. Okay. This is equivalent to the top is just the thing what we did up here originally. So we just have y bar sub 1 minus y bar sub 2 minus mu sub 1 minus mu sub 2, all divided by sigma times the square root of 1 over n sub 1 plus 1 over n sub 2, and then that's our numerator, and that's all going to be divided by the square root. If I combine these two terms together, nu is the degrees of freedom that we see here. So it's like multiplying or dividing by that degrees of freedom. So we end up getting the chi-square w value, which is n sub 1 plus n sub 2 minus 2 times the pooled standard deviation squared, all divided by sigma squared times n sub 1 plus n sub 2 minus 2. I'm skipping a step there, obviously. That was that whole thing divided by it, but it ends up shoving it in the denominator when we flip everything around. So when we simplify this thing, we get the actual t-score value for a t random variable, which just becomes y bar sub 1 minus y bar sub 2, excuse me, minus mu sub 1 minus mu sub 2, all divided. Some things cancel out on us. The sigma squared cancels out with this sigma here. If we take the square root of sigma squared, pull it out, those cancel each other out. These guys cancel each other out. and we're left with the pooled standard deviation, so we just get S pooled times the square root of 1 over n1, n sub 1 plus 1 over n sub 2. And that is where the t pivotal quantity comes from for a pooled standard deviation, and it's assuming that the population variances are equal. I just kind of think that's neat to see. So that's all we're going to say about that. But we're going to have to use that formula nonetheless. So we're going to do that right now. So it's a rather long-worded question or problem. So to reach maximum efficiency in performing an assembly operation in a manufacturing plant, new employees require approximately a 1-month training period. A new method of training was suggested and a test was conducted to compare the new method with the standard procedure. All right, so 2 groups of 9 new employees each were trained for a period of 3 weeks. One group using the new method and the other following the standard training procedure. The length of time in minutes required for each employee to assemble the device was recorded at the end of the 3-week period, and we can see those values in the table. So obviously we got to do some work. We got to probably find the means and the standard deviations for the 2 different groups separately so that we can construct our interval. But they want us to estimate the true mean difference, mu1 minus mu2, with confidence coefficient 0.95. Assume that the assembly times were approximately normally distributed and that the variances of the assembly times were approximately equal, so that we can assume that the population standard deviations are approximately equal for the 2 methods and that the samples are independent. That independence is another thing we have to note too, that samples must be independent of each other. So we got everything we need. I will skip over showing you where to get the mean and standard deviations from. So from R, when I did this, I got the y bar for the first group, which is the standard group, was equal to 35.22. And for the other group, the new procedure, y bar sub 2, I got that was 31.56. And then the standard deviation, or the variances for both groups, S1 squared was equal to 24.444. And the variance for the new group was 20.028. All right. The sample sizes for each one of these guys was n sub 1 was 9 and n sub 2 was also 9. So both groups had 9 individuals in them, and we have a confidence level of 0.95. All right. So the degrees of freedom for our test is going to be n sub 1 plus n sub 2 minus 2. So it's basically 18 minus 2, so we get 16 for our degrees of freedom. All right. And then our critical value, t sub alpha over 2, should be just, since we're doing a 95% interval again, it's going to be qt in R, and 1.95, 1 plus 0.95 over 2, and the 16 degrees of freedom, and that gives me a critical value of 2.120. So now I have everything I need to plug into the formulas that I need. So before I can construct the interval, I've got to figure out what the pooled standard deviation, or the variance is, or standard deviation really, because we're going to take the square root of it. But SP squared is the formula they give us. So I need to figure out what SP squared is, and that's going to be equal to n sub 1 minus 1 times s sub 1 squared plus n sub 2 minus 1 times s sub 2 squared, all over the degrees of freedom, n sub 1 plus n sub 2 minus 2. All right, and that equals n sub 1 minus 1 is 8 times its standard error of 24, or standard variance of 24.444, plus n sub 2 minus 1 is also 8 in this case, and s2 squared, s sub 2 squared is 20.028. You got to really watch these problems on whether you have the variance or the standard deviation to make sure you plug in the right values here, because this formula takes in obviously the variance, not the standard deviation. So if you're given the standard deviations, make sure you square those things, and that's going to be divided by 16, and that gives me 22.236 for the pooled variance, but the pooled standard deviation, SP, is just the square root of that value, which is equal to roughly about 4.716. So I'm going to need that value here shortly. So now we can finally construct our interval. So y bar sub 1 minus y bar sub 2 plus or minus the critical value times the pooled standard deviation times the square root of 1 over n sub 1 plus 1 over n sub 2. And that gives me y bar sub 1 is 35.22 minus 31.56 for y bar sub 2, plus or minus the critical value of 2.120 times the pooled standard deviation of 4.716, finally times the square root of 1 over n1, which is 9, plus 1 over n sub 2, which is also 9. And finally we can calculate these things out. So you should get the difference between the means should be 3.66 plus or minus, and multiplying all that stuff together after the plus or minus, we should get 4.71 if you round to 2 decimal places. And so a 95%, if I can write a percentage tonight, percent confidence interval for mu sub 1 minus mu sub 2 is equal to negative 1.05 and 8.37 minutes. That was what they were being timed for their assembly. So apparently there's not a distinct difference between the standard and the new procedure as far as the number of minutes it takes them to complete their task, because we have a negative bottom end and a positive top end, so there's no significant difference there that we can say that one procedure is truly better than the other. All right, we won't interpret that any further than that, but that's a pretty good interpretation of an interval like that. This last example I want to do is going to use the other version of the formula. We're going to assume here that the variances are unequal. All right, and this is almost is equally tedious because of the formulas we have to use for the degrees of freedom. So here we say a survey of college students reported that in a sample of 413 male college students, the average number of energy drinks consumed per month was 2.49 with a standard deviation of 4.87. And in a sample of 382 female college students, the average was 1.22 with a standard deviation of 3.24. Construct a 99% confidence interval for the difference between men and women in the mean number of energy drinks consumed. Assume that the number of drinks consumed are approximately normally distributed, that the variances of the number of drinks is not equal for the two groups, and that the samples are independent. Based on the confidence interval, is it reasonable to believe that the mean number of energy drinks consumed may be the same for both male and female college students? Well, we'll find out. So all the information we gave, and we have the sample size for the men, which was 413, and the sample size for the women, we'll just call them female, was 382. The sample mean, y bar sub m, was 2.49 for the men, I believe. Let me double check that. Yes, the mean drinks for the men was 2.49, and the mean drinks for the women were 1.22. Standard deviation for the men was 4.87. It's pretty wide variance, but the women's was not that much shorter of a standard deviation of 3.24. And then the critical level they wanted us to reach was 0.99. Okay, so before we figure out the T alpha over 2 value we first need to find the degrees of freedom. And so if you do, you have to start with the C formula I gave you on that slide a few slides back, which says, in this case, it's the whichever group 1, which is we're going to put the men first, S of m squared over n sub m, so the variance of the men over the sample size of the men, divided by variance of the men divided by the sample size of the men again, but plus the variance of the women over the sample size of the women. That's the formula we got to solve first. So that's going to be 4.87 squared divided by 413 in the top over 4.87 squared over 413 plus 3.24 squared over 382. And when you calculate that thing out, you get some crazy number, 0.676343. I recommend rounding that off to 6 decimal places so you can be as close to the technology as possible. Okay, at least what computers would do for us. So the degrees of freedom formula is the next thing we have to do, because C is involved in that. And that's going to be the sample size of the first. It's basically the degrees of freedom of the first group times the degrees of freedom. And I think I used women over there. I changed it up. My bad. This should be female up here. Minus the degrees of freedom of the second group. All right, all divided by 1 minus C squared times the degrees of freedom of the male group plus just C squared times the degrees of freedom of the female group. All right, so I'm going to get in this long-winded thing here, and so we get 1 minus 0.676343 squared times n minus 1, so n sub m minus 1, which is 413, plus 0.676343 squared times the degrees of freedom for the women's or the female group, which is going to be 381. And then the top, we just get that 413. Sorry, not 413. I caught myself there. It should be 412. 413 was the sample size. The degrees of freedom should be 412 here. So it should be 412 times 381 in the top. And that's approximately equal to some outlandish degrees of freedom of 721.899. So you're probably asking yourself, usually our degrees of freedom are in whole numbers. Well, it just turns out that whether you're using the calculator to find your critical value, T sub alpha over 2, or you're using R to do it, you can use numbers that aren't perfect, whole numbers, to find your critical value. So I'm going to say round this value off to at least 3 decimal places, like I did, and then your T alpha over 2 value should be 1 plus the critical value, which will be 1 plus 0.99, 1 plus, or 1.99 divided by 2, comma the degrees of freedom of 721.899, and that gives me a critical value of 2.583. Now we have everything we need to plug into our formula. So the difference between this formula, this confidence interval formula, and the last one was we can take the y bar of the first group, the males, minus y bar of the females, plus or minus the T alpha over 2. Everything looks the same so far, but now we're going to multiply that by the square root of the first group's variance over its sample size plus the second group's variance over its sample size. So that gives us 2.49 is the mean of the males, minus 1.22 drinks on average for the women, plus or minus the 2.583 times the square root of the standard deviation for the sample standard deviation for the men was 4.87. I'm going to square that and divide it by its sample size of 413. Plus the women's standard deviation was 3.24. We got to square that and divide that by 382, the full sample size. So when we do that, we get 1.27 for the difference between the means, plus or minus roughly about 0.753, which just gives us the confidence interval, or the 99% confidence interval, of 0.52 on the lower bound to 2.02. So both positive numbers, drinks per week. All right, or I think that's what they were looking at. Okay, so there's your answer for the confidence interval. But they had a backup question which said, based on the confidence interval, is it reasonable to believe that the mean number of energy drinks consumed may be the same for both male and female college students? Since both of these values came out the same, no, it's not reasonable to believe that they're about the same. If it was if a negative bottom value to a positive top value, then we'd say yes. But since they're both positive, it means the men on average drink more. So we say no. Both values are positive. Which tells us the men drank more energy drinks on average. And I'd like to think that we probably figured that out without doing a confidence interval on it, but the confidence interval backs this up and proves that it's true. I would like to say that probably more men do that, drink more energy drinks than women. Okay, so that's basically the T intervals, the three types that you'll see. I will always tell you whether to assume that the variances are equal or not equal in our graded homework, so don't worry about that. The key to it is that this one did have a pretty large sample size, but if you're ever given the data straight up like I did here, if you're ever given the data set, you probably can assume I'm asking you to do a T. All right, they just gave the values here, and so again, the sample size, we can do a T with any sample size we want, but that's neither here nor there. But I guess what I'm trying to say, I'm dancing around this subject. If you see a small enough sample size, always do a T. When you see a bigger sample size like these, you might be able to get away with doing the Z interval. But if I explicitly in a problem say assume the variances are unequal, the population variances are unequal, or you see sigma 1 squared is not equal to sigma sub 2 squared, then I'm probably asking you to do this method right here. All right, just heads up. I don't want there to be any kind of fuzzy cloudiness around that or whatever. All right, so for recommended textbook exercises in section 8.8, do problems 81, 85, and then do problem 90, but do only part A, and assume the variances are not equal and use the Welch method. Okay. I will go over the solutions in the next lecture. So hope everybody's having a good one. We'll talk to you later.